Again, I just want to thank everyone for attending our webinar. Today we're going to do some advanced principal components analysis. We're going to do some information about projection and how SIMCA and how to look at some stability plots to see if you have some data points that are specifically out of whack and throwing off your models. So just a brief overview to go back over our principal components analysis just to make sure everyone is on the same page. So when we do a principal components analysis, we have our X block data. We're looking at our X block to understand the space of our data, to extract the information, remove your noise, and really do some exploratory data analysis. You can also use principal components analysis to reduce your dimensionality of your information for classification and identification purposes, variable reduction, and process monitoring. And so we take our original Rx data, and from that we get our model and our error. So that's the original data. You get your structure and your noise. And depending on what your specific application is, your structure and your noise may be different. In certain cases, what is noise in one case might be structure in a different case. So just always make sure you're aware of that when you're going through your information analysis. And so what we have here is our PCA overview that shows up in the unscrambler. You have a quad plot, and so you have your scores space, which you can then take your data and group it color-wise based on different groupings that you may set up. And then we have our loadings plot. In this case, it's showing the correlation loadings. So this gives you a way to interpret your loadings and your scores and your data to see what samples are being affected by what variables and what the variables mean and how they correspond to your principal components. We also have our influence plot in the bottom left-hand corner, which that's going to have your F residuals or your Q residuals to show how much of the data is left over, so how much noise is left after that number of principal components. And your hoteling t-squared, that tells you how close your sample is to the center of your model. In your lower right-hand corner, we've got the explained variance chart. This is where you start when you're looking at your principal components and you're doing your interpretation, because you first want to look at how many principal components you want to use. And that's how you can tell that. So just a reminder of what the scores and loadings are. Your scores are the map of the objects, so your individual samples in the principal component space. So your score is how far along the principal component each individual sample is. The loadings is a map of the variables in the principal component space. So this tells you which variables are contributing to the different principal components. So in this case showed here, variable 1 is strongly positively correlated with principal component 1. So any samples that have a high score on principal component 1 have a high value in this variable 1 in this particular case. So one thing we like to look at when we are doing principal components analysis is when you're doing a cross-validation, all your submodels can be displayed. And then you can see these plots of stabilities. You can look at the stabilities of both your scores and your loading plot. If you're stable, then there's less chance of outliers, and the model changes, but the model doesn't change if you take that out. If there is an outlier, this will show up here, and you can see that it disturbs the model and it is an outlier. So in this case, you can see here there's one very large change here. And so what we see is that this particular point, number 4, Belgrade, is causing a big issue in our stability. So again, we can look at the stability in both your scores plot and your loadings plot. So you can see if there's a particular variable that's not stable. So there's an outlying value in this particular variable. In this case, November, for some reason, if we're looking, it shows a very distinct difference between the other ones. So let me go to the unscrambler and we can take a look at this data set and how you would get these stability plots. So the data I'm loading here is a survey of different European cities and their temperatures over the year. So first thing I always do is you plot your data just to get an idea of what is going on. So we're going to plot our temperatures for all our different rows. And we see here there's a general trend that you would expect, right? So you have lower temperatures in the winter months and then higher temperatures in the summer months. We do see there's one a little bit strange here, November, where there's an increase that you maybe would not expect. If you want, we can right-click and do sample grouping. We can make a grouping based on the region. If we drop down our columns for region and create row sets, it gives us our different regions that we had labeled in the category variables. We bring them all over, and we can see this here. And what we see is what you might expect. So your overall higher temperatures are in the south, and your Nordic cities are in the lower temperatures, even though they follow the same general trend. So now let's do a principal components analysis under Tasks and Analyze. We want to do the temperatures. We're going to do all rows. And under Validation, you want to click this uncertainty test. Make sure that that is on, and that's how you'll be able to get the stability plot. We'll check the setup and make sure we do a full cross-validation because we have less than 30 samples. And here's our general plot. So the first thing we want to do, again, is look at your explained variance to figure out how many principal components you would want to use. In this case, we might want to use up to 3. You're not going to get any more information after 3, so no more than 3 in this case. We can take a look at our loadings here. In the top, we can switch through the individual principal components and take a look at them, but we can also look at all of them at one time if we highlight in there and type in the number of variables we want to look at. Turn on our legend and we can see principal component 1 looks like when it has higher temperatures in the winter months versus the lower temperatures in the summer months. That's going to be what is happening there. I'm going to put my labels on here. And we can see all of our scores fall pretty well inside the space. Now, if you want to look at the stability plot that I showed you, there's a little button right in the middle above next to the hoteling T-square ellipse called the stability plot. And if we click on that, you can see, I'll turn the labels back up, you can see how each individual cross-validation shows up in this case. Now what we see here is in principal component 1 and 2, everything looks fairly stable. But if we increase to principal component 3, you can see very quickly that there is some differences going on. So we can frame scale go in here, and you can see how unstable, especially this particular point is. And that's number 4, which is Belgrade, which we showed earlier has a slightly different space. Now if we go back to the loadings, if we look at just PC1, And we change this to, sorry, trying to change my loadings to a scatter. We can also look at the stability in there. And so you can see there is some instability in March here. And if we go up to PCA 3, there's some large instability in the November, which if we go back to our line plot, put the sample grouping back on, we can see here this is that November in Belgrade. So that makes sense. And that's a way of identifying where you have some instability in your data. So let me go back to the slides. So another thing that we like to do with principal components analysis is that we want to do projection of new samples. So it's great to use for exploratory analysis, but it's also helpful for projection of new samples. So say you are working in a pharmaceutical environment and you have new materials coming in. You want to be able to say what if this is good or if it's bad, or identify different types of chemicals from each other. And you do that by doing projection. And so once you've built your model, let me get this back up. Once we've built our model by taking the data and getting your scores and your loadings, then what you can do is you can predict new scores from your new X data and put it with your loadings, and that gives you your new scores output. So it's a very basic form of multivariate classification. And basically in this case what you're wanting to do is check to see if your new samples lie in a similar space as the original model or if they're different. So how does the projection work? So you collect data on training samples and you build your model. So you look at your loadings, your variable relationships, and then you get your scores with a hoteling t-squares ellipse showing the acceptable limits for new samples. So each one of these is the sample making up your original principal components model. These are your calibration samples. So then what we do is collect new data on new samples that you know. They come in, you put it into your model, and you project what your new scores are going to be. And so here you're seeing projected samples that are within your acceptable limit. So you would say that these samples are similar to your calibration data set. Now, if you have samples that fall outside of this eclipse, those are suspect samples and they require more attention. They may still be good samples depending on how close or far away they are from your data, but when it's outside of this hoteling t-squared ellipse, you want to look a little bit further at your data to see what's going on with those particular samples. How different are they and why are they different? So I'm going to show you another example. I'm going to open up some oils. So this data that we're looking at is some near-infrared spectroscopy on different types of oils. So we've got some corn oil, some olive oil, safflower, and corn margarine. Again, first thing I do whenever I get new data in is I plot it to get a visual idea of what's going on. So I'm just going to do a line plot here. And then I'm going to group my data again. You're going to right-click, sample grouping, and then we have some available row sets because we had those that category variable in there. Going to pull those over, and we can take a look and see what is going on here with our data. As we can see, they follow a general similar shape, which we would expect from oils. And we might want to zoom in and look at some different areas to see if there's anything major changing. We can see here, if I put my legend on, corn margarine has a peak here that nothing else has, and there's some differences in the ratios of the peaks between the different types of data, types of oils. We also can look here to see if there's any sort of shifts that are happening, and we can see very clearly there is a baseline shift that's happening. These samples were taken over a long period of time, so sometimes your instrument may drift a little bit, or you have slightly different samples, but they have a general same shape. So first thing we want to do is let's do a principal components analysis on the raw data. We want to use the spectra. Leave the uncertainty test and do a random cross-validation is fine. That looks a little strange to me. Give me 1 second. I'm not sure what happened there. Test, analyze, principal components. All right, well, we'll look at our explained variance. It looks like it only is taking us to principal components 5 at the moment. And what we see is I would probably stop around 2 principal components because that explains about 94% of our variance. And going up to principal components 3, you see there's a leveling off here. It doesn't give us any more information. We can look at our loadings and we can see that our CH peaks, which we would expect, are showing the major differences in these loadings. We can flip through, see what loadings 2 is. And so we see a lot of information that's coming out down here in those fingerprint regions of the IR data. If we take a look at our scores, we can do sample grouping based on our types of oil. Oh, I know what I did here. Let me go back. Pardon me. I wanted to do principal components on the calibration set only. Now we converge. So again, in this case, we're probably only going to use 3 or 4 principal components. So we've passed that 95% confidence interval. If we take a look at our sample grouping here, we can see that they separate pretty reasonably. We've definitely separated out the safflower oil, the corn oil, and the olive oil. The corn margarine sort of overlaps a little bit with the olive. And so if we take a look at principal component 1, we can see that they generally, the trend here is the ratios between the unsaturated and saturated fats in the oil. So you can say that the olive oil here has, I believe it's less saturated fat, and then as you move this way, we have more saturated fat as we go towards the safflower oil. It looks like all of our samples are well within the model. We have no outliers. But what we do notice is most of the changes are happening down here in the lower regions. So one way we can look at this, more importantly, is if we mark with our rectangle we can highlight those. Now we can go to the principal components analysis on the left here, right-click, and recalculate with the unmarked downweighted because they're not necessarily as important for separating these out. You can press OK. As we see, we can get we're getting a little bit more information with fewer principal components. Get our sample here. We have a slightly better separation, but not so much with your corn margarine again. So now what we're going to do is go back up and look at, we're going to rerun this. First, we're going to take a look at those scattering effects that we saw. If we analyze using our descriptive statistics, and we want to look at spectra. Now this comes up, these are our quantiles. So let me zoom in and show you a little bit what they are. So these are box plots of the individual variables. It shows you your mean, or the median, the quartiles, and then the full range. So that inside the box contains 75% of your variation. On the bottom here, you have your mean and your standard deviation at each wavelength. Now, if we right-click, we can get this statistics scatter effects. This is really helpful for identifying what sort of pre-processing you might want to do. On this drop-down menu, you want to go all the way down to all. And what we can see here is you see a general trend that they are following the same slope, essentially. There's a little bit of slope change as you get up here. There's also an offset. So what we can see from this is that if all these lines are the same slope and parallel to each other, then these are additive effects, mostly. If there is a fanning, which we see a little bit up here, where you have a larger spread than you do at the bottom, that tells you that there are some multiplicative scatter effects as well. And if you're having significant chemical effects, you'll see kind of loop-de-loops in here. But in this case, it's showing that each spectrum is very similar to the other ones in the general shape. So there's no real major chemical differences that are happening. So what I'm going to do is I'm going to apply a standard normal variate, and I'm just going to do those specific wavelengths that are down on that look at the ratio between the double bonds. So if we take a look at this again, let's plot. We're just going to do the specific and our calibration samples. And we can see very clearly that we've taken out a lot of those baseline issues. And each of the samples are very much closer together. So we've taken out a lot of the noise by doing this pre-processing. So if we take that signal noise variate, and now we do a principal components analysis on that, just on the specific ranges, you see we now have a 2 principal component model, very clear separation of all our different types of oils. Well, now that's great, right? So we've got good separation. We do see that with our hotellings, we have 4 samples here that seem to be far outside of our model. If we do our sample grouping, we will see that these are actually those corn margarine samples. Now this just says that they're different from the rest of the samples. And in this case, for corn margarine, that's actually heat treated, so you have some trans fats in there, and that's what's showing up in this particular case. Now, what if we have new samples? So I promise you projection. So the way we do that, in the unscrambler, when you run an analysis, it always keeps the pre-treatment that you've done. So this principal components model will automatically apply signal-to-noise variate on any new samples that you predict. So when you do this, you want to make sure to use your raw data again. You go to tasks, predict, projection. And now we're going to use our matrix oils. We have some test samples here. And we're going to use those specific wavelengths. Oh, pardon me. Predict projection. We do want to make sure that we use the correct principal component. So this is the one that we did with the SNV. We want to do our test and those specific wavelength ranges. And here we can see that our residual variance is very close to the original, so that shows that these are pretty well predicted. Our loadings are the same as we saw before. And in our scores plot, what we see is that the blue samples are our calibration samples, and the green ones are our test samples. If I put on our labels, it's a little messy, but we can see that all the olive oil showed up there. The corn margarine, if I zoom in, you'll be able to see that they are properly identified. It's not working. Let me drag this. So you can see the corn margarine is in there. Auto scale. Corn, and now this is interesting. You see some soybean oil that is overlapping with corn. So that tells us that it's probably similar in the amount of saturated and unsaturated fats that it has. We've got the safflower oil, and then we've got our other new samples. We've got walnut, sesame, and peanut. So you can see they separate again along PC1, which we determined is due to the different amounts of saturation of the fats and the bonds in there. Slides. All right, so the next thing I'm going to talk about is SIMCA. This is a way of classifying your data, and it takes advantage of the similarities of the members of the same class. So what you do, and I'm going to show you an example of this with the oil, is you build a principal components model for each class, which defines the principal component space for each class. And then samples that are well described by that particular model are accepted based on your residual and your leverage, and others are rejected, not classified. So you can use a global PCA to determine the existence of classes. That's what we just did in our oils example. And then you make individual models based on those samples to establish limits around those groups. And then that develops a library of models to apply to new data. So how do we define class membership? So we first get our samples. So in this case, I believe we're looking at octane amounts. And so we look at all of the ones that are high octane levels. And we look at the direction of the maximum variation. And then you find the center of the model. So you find the critical leverage. That's going to be your Hotelling's T. So how far out for your 95% confidence interval, for example. Define that. And then you find how far away from that space is a critical distance. So that's going to be your residual direction. And then you define a cylinder of class membership. So basically anything now that falls within this ellipse is going to be considered part of the class of high. And anything that falls outside of this ellipse will be excluded from the class. So this is just an example of classifying new samples. So you've got your model samples in blue, your calibration samples, and then your red samples are the new ones. And you see a number of them fall within that space and are classified as class 1. And then you have these few that are out here that are unclassified because they don't fall within that model space. So there's a couple of plots that we look at um, in SIMCA, and one of them is called the Kumans plot. And what this does is it looks at the distance from the models for two different models. So you've got sample distance to model A versus sample distance to model B. So anything that has a very large value on this x-axis is not close to model A. So once it's past this limit of membership, it's saying that it's not part of class A. And the same thing for model B. So anything that is in this upper right-hand quadrant is going to be samples that don't belong to any models, and it will just not be classified. Things that are in the lower left-hand corner are samples that belong to both models. So basically it would say that those particular samples cannot be distinguished whether they're within model A or B because of similarities of both. Ideally, all of your samples that are model A will fall up in this area in the top left-hand quadrant, and all samples belonging to model B will be in the lower right-hand quadrant. Another thing that we can look at is for each individual class membership, we can look at the residuals and the leverage. So this is going to be more like what you're used to seeing in a principal components leverage plot, where in the lower left-hand corner, these samples belong only to model A. If they are far to the right, they're going to say they are part of the model, but they have extreme properties. So they're far away from the center of the model, but they're still within the space. If they have a high value in the residuals, they may still belong to the model, but they're spectrally different. There's some residuals that are different in that case. And then anything that's up in the upper right-hand quadrant are not members of Model A. That's what we tend to think of as outliers when we're looking at principal components analysis. And then your final output is going to be this class ambiguity classification table. So the classification table will take every sample that you put in and make an asterisk for whichever model it has decided that it's a member in. Ideally, a single sample is uniquely classified. So there should only be a single asterisk along each row. Every now and then, you're going to have some ambiguous situations, and you'll have more than one asterisk. And then in this case is when you can resolve this by using hierarchical models. So there may be different ways that you want to look at. In this case, we have some ambiguity between this M0643 and M4642. So we might build a model that just looks at those two to try to separate them after we've already identified the global system. So I'm going to show you how to perform SIMCA using the unscrambler. So I'm going to go back to this principal components space. And what I'm going to do is I'm going to highlight my samples. You can use this rectangle. Highlight here. Now if you go to the principal components in the left-hand side, if we right-click, we can recalculate with marked samples. That will recalculate this principal components analysis using only those samples. And we're going to rename this as corn. And we're going to do this for all 4 cases. We're going to unmark all, and then we're going to create a new one with marked samples. This is the safflower. Rename. Mark all. We're going to do this. Now we have the olive. And one last one. Unmark all. And this is our corn margarine. So once we have done that, now we want to run a SIMCA classification. Under tasks, we want to do predict, classification, SIMCA. Now remember, you want to use your raw data. Again, we are going to use our test set using those specific columns. Now we want to go and choose all our models. So we've got corn, we're going to add that one, safflower, olive, and corn margarine. We're going to say OK. And here's our results. So as we see, all of our corn, with the exception of one, are labeled as corn. Safflower is labeled except for one. Olive is all labeled except for one. All the corn margarine are correctly identified. And then soybean is being considered part of corn, which makes sense because that's what we saw earlier in our principal components. So you might want to look a little bit further. You can change the acceptance values. If we say we only want to be 10% sure that it's included, now we have no misidentifications of the soybean oil. We can make it a little bit more firm. And there's no real changes there, but we can make sure that those are not included. So that's our classification table. We can look at our Cummins plot, and this will show us all of our different data points. The blue and the red here are your calibration samples, just to show where they fall in the line, and the green are the newly predicted samples. In this case, we're looking at safflower versus corn, and we can see all of the safflower falls in the space and all of the corn falls in the space, and that's where you see that soybean is falling within the corn as well. But if we change that limit, it moves in and it pulls that out. That's why we are seeing that happen. Again, we can look at our individuals. So we've got these corn. So these corn are all falling in here. We've got one corn that is probably the one that was not identified correctly as corn that has a high leverage. And then the soybean is falling in here, but none of the other ones really are. There's a couple of saffron that are on the edge of your leverage in that case. So that finishes up that example. So I just want to reiterate some basic rules in multivariate analysis. You always want to make sure to use a representative calibration and validation data. Make sure you have enough samples spanning all your major variations. Select an appropriate validation method. In this case, we're doing cross-validation. Ideally, you would have a calibration set and a test set, which is what we did as well. Look for your outliers. If you have any extreme samples, you have to look at them more closely to determine if you want to keep them or remove them. Some may carry information, and sometimes they have erroneous data, so you have to make a judgment call in that case. You want to select the correct optimal number of principal components. You don't want to take too many principal components or you get into the place where you're modeling noise, but you don't want to take too little because you want to make sure you're incorporating all of your information. Take a look at any patterns in your data. You can see that in your scores or your loadings. Also look at your variable relationships. Understand what your loadings are based on your variables, especially in spectroscopic loadings. You want to make sure that you're not seeing noise. If the loadings look like noise, they probably are. You want to be able to interpret your loadings. Make sure to be careful with transforming and pre-processing your data. Make sure you know why you're doing it. If you see some scattering, make sure you look at whether it's additive or multiplicative, so that you are making conscious choices of your pre-processing, not just doing a black box. And then you check how well your model will perform with new data by studying your validation. That was your test set, like we show. And as we always say, practice makes perfect. There's always an ongoing learning process with multivariate data analysis. And that is all I have for now, so I will open up to any questions that you might have. You can type them into the box and they will come to me and I will happily respond. All right, looks like I'm not getting any particular questions at the moment. Oh, here we go. Is it appropriate to use SNV when you have large chemical differences between the samples, unlike the oils? Sometimes, yes. You have to take a look. You can still have baseline shifts and additives. The way SNV works is it works on each individual sample. So it will take the mean of a spectrum and divide it by the standard deviation of that spectrum. So basically what that does is it's almost like a baseline offset. So it's not going to change your chemical information. It's just going to bring everything down to the same scale. What is the difference between SIMCA and SVM? So SVM is support vector machines. They work very differently. SIMCA looks at, uses principal components models for each individual class, where the support vector machines, it's usually used for nonlinear deviations between, or separation between classes. But that's another topic that I can do a webinar on at another point. For multivariate analysis, can the responses be dependent on each other or have a correlation relationship? And sometimes the responses are related to each other. It depends on how similar your samples are to each other. Like we saw the, was it the soybean oil falls near the corn oil. So they can show up similarly even if they aren't the same types of data. In the slide with the spectroscopic data, I've noticed big variance in the beginning, but you zoomed in at the end. I'm not sure what you're asking there. I think, are you talking about how I reduced the variables? So let's take a look at these line plots. So I'm guessing what you're asking is about the changing the amount of the wave numbers that we're looking at. And that's mostly because you can see in, let me get my sample grouping going here. There's not a huge difference in these areas. Oh, having troubles here. They're very similar in these areas. There is a couple of differences, but they're more of an offset. But most of the information in these particular samples is held down here. And if you can reduce the number of variables and still get a good classification, then that's a good thing. Then that's better. It makes it more simple. And the simpler the model, the more robust it's going to be in the future. All right, I am recording this, so I will put this up on our website after this is done and send you guys a link. If you have any further questions, please feel free to contact me. My email is hbrooke, B-R-O-O-K-E, @camo.com. I'm happy to help you with anything that I can. I hope everyone has a great day.